Data science regression techniques are essential tools for answering one key question. That is, how does one variable affect another? At their core, all regression models try to model the relationship between input variables, also known as features, and an output variable, also known as target, usually with the goal of finding or making predictions or understanding influence. So there are some common regression techniques like linear regression, logistic regression that we're going to discuss in this module. And then there's also additional regression techniques like polynomial regression, ridge and lasso regression, decision tree-based models, support vector regression, or neural network for regression. That is outside the scope of this class, but I want to expose you to all of the other techniques, such as polynomial regression is a more flexible version of linear regression that fits curves instead of straight lines. It's useful when the relationship between variables is nonlinear but smooth. And then ridge and lasso regression, they are regularized version of linear regression that prevents overfitting. Ridge shrinks coefficients, and lasso can shrink them all the way to zero. So that's often used for feature selection. And decision tree-based models like random forest and gradient boosting, they are powerful, nonlinear, and great for complex real-world data. And they can handle mixed data types and capture interactions between features. And support vector regression, it's a robust regression method using support vectors and margin-based loss. It's good for high-dimensional and small data sets. Neural network is ideal for very complex and high-volume data when traditional methods fall short. It can approximate any function but require more data and tuning. Among all these tools, generalized linear models stand out as a powerful extension of linear regression that bridge the gap between basic statistical models and more flexible machine learning techniques. GRM provides a unified framework that allows us to model different types of outcome variables like continuous, binary, count, or skewed. You can choose the appropriate distribution for the outcome, like normal, binomial, or Poisson. You need to apply a link function to connect the mean of the outcome to a linear combination of inputs. So GRMs are important because they generalize traditional linear regression to handle non-normal targets. They are widely used in healthcare, economics, marketing, and social sciences, where interpretability is crucial. They form the statistical backbone of more complex models like logistic regression, Poisson regression, or gamma regression. So these are all examples of GRMs. They're especially useful when you need transparency, hypothesis testing, and reliable inference. Whether you are forecasting revenue, predicting user churn, or modeling disease risk, regression models give you a lens to quantify relationships and make informed decisions. GRM extend these lens to a wide world of data types, making them a core technique every data scientist should understand. Right. Let's kick off this topic by talking about why we use regression in the first place. What makes it such a powerful and essential tool in analytics? So first, let's start with linear regression. At its core, linear regression is a method we use to model numerical outcomes. In plain English, that means we are trying to predict a number like a person's salary, house price, or number of items sold based on one variable we know based on other variables we know about them. There are two basic types. Simple regression involves just one predictor. So maybe we're just looking at how one factor, like years of education, predicts salary. And then multiple regression, on the other hand, include several predictors like education, experience, and maybe even zip codes working together to estimate salary. The mathematical forms of linear regression look like f of x equals to beta t multiplied by x vector. So beta t vector is the coefficient vector. So essentially, it just means we sum up all our variables x weighted by their respective coefficient beta. Now, linear regression is great for continuous outcomes. But what if the thing we are predicting isn't a number, but a category? For example, will a customer buy something or not? Or is a tumor benign or malignant? That's where logistic regression comes in. This is what we call generalized linear model. Instead of modeling a number, we are now modeling the probability of an outcome. In the binary case, we predict something with two possible outcomes, yes or no, success or failure. There's also a version that handles multiple categories, like classifying a product review as positive, neutral, or negative. Whether it's linear or logistic regression, the key idea is the same. We're estimating model parameters. Those are the beta coefficients, and we want to understand what they mean. For example, if beta 1 is the coefficient for years of experience, it might tell us that for each additional year of experience, the salary increases by 2,000, holding everything else constant. So to wrap it up, regression is all about building a mathematical relationship between the outcome we care about and then the variables that might explain it. It's simple but extremely powerful, and the foundation for so many predictive models we will explore later. So now that we know what regression is and what it's trying to do, let's talk about the ground rules. These are the assumptions that linear regressions make in order to work properly. If these assumptions are broken, the results we get may not be trustworthy. Let's go through them one by one. First, there need to be a linear relationship between the independent variable and dependent variable, IV and DV. In other words, the connection between x and y should look more or less like a straight line, not curve, not a zigzag. We can check this visually with a scatter plot. If the data points seem to follow a straight line, great. If not, we might need to do some kinds of transformation. For example, maybe the relationship becomes linear when we normalize the dependent variable or take the log of it. Second, homozygoticity. And yes, that's a mouthful. This just means that the spread of the errors or how far off our predictions are should be roughly the same across all levels of our independent variables. Imagine trying to predict someone's income based on age. If your prediction errors are all over the place for older people, but very tight for younger people, that's a problem. We check this by plotting residuals versus predicted values. What we want to see is a nice, even cloud of points, not a fan shape, cone, or pattern. Third, multivariate normality. This one is a little more technical. That means the residuals, which are the differences between the actual values and the predicted ones, should be normally distributed if we want to make accurate statistical inferences. You don't need a perfect bell curve here. but serious deviations from normality can affect confidence intervals and p-value. And then fourth is independence of error terms. This means the errors shouldn't be correlated with each other. In simple terms, knowing one residual should not give you any clue about the next one. This is especially important in time series data or when variables are closely related. We check for this using something called VIF, variance inflation factor. If a if a variable has a high VIF, typically above 5 or 10, that's a red flag for multicollinearity, which means the predictors are too similar to each other. So linear regression is a powerful tool, but it comes with these built-in assumptions. If we ignore them, we risk making wrong conclusions or poor predictions. Luckily, most of these can be checked pretty easily, and we have techniques to fix them when they don't hold. Now let's talk about one of the most popular metrics in regression analysis, R squared, also known as the coefficient of determination. At a high level, R squared answers a simple but important question. How much of the variation in our outcome can be explained by our model? So if your R squared value is say zero point 0.8 or 80%, that means 80% of the changes of variability in your Y values can be explained by the X values in your model. The remaining 20%, that's randomness, noise, or stuff your model just didn't capture. Now let's break down the math a little bit. But don't worry, it's not going to be too bad. So first, we have TSS, that stands for total sum of squares. That measures how much the actual values vary around the average. That measures how much the actual values vary around the average. So this is the total variability in the outcome Y. Next is SSE, or sum of squared errors, sometimes also called the residual sum of squares. This is how much error your model is making in its predictions. So we are comparing the model's predicted value, f of x sub I, to the actual value, y sub I. Then we get SSM, or sum of squares due to the model, which is simply TSS minus SSE. That tells you how much of the total variation the model was able to explain. Finally, we calculate R squared using the formula R squared equal to SSM over TSS. Right? So again, this is just the fraction of the total variation that our model actually captures. So imagine you are trying to guess people's heights based on their shoe size. If your R square is 0.9, it means you are doing a great job. 90% of the variation in height is explained by shoe size. If it's only 0.1, well, your model isn't very helpful. You are basically guessing most of the time. Just because R squared is high doesn't always mean your model is great. It might be overfitting the training data. So R squared is useful, but always consider it alongside other diagnostics, especially when you are building more complex models. Let's now talk about how regression actually works under the hood. Specifically, we are going to look at something called ordinary least square, or just OLS. So here's the big idea. OLS try to find the best fitting line through your data by doing one main thing, minimizing the sum of squared errors. What does that mean? Well, for each data point, there's difference between the actual value and what the model predicts. That difference is called an error or residual. If we square each of those errors to make them all positive and emphasizing big mistakes, and then add them all up, we get the sum squared errors. OLS works by finding the line, the set of regression coefficients that make this sum as small as possible. So in short, OLS is equals to let's draw the line that makes the total squared mistakes as tiny as possible. Now, how do we actually estimate the coefficients? There are two main approaches. One is closed form solution or analytical methods. This is the traditional math-heavy way. We use matrix algebra to solve for the coefficient directly. It's neat, clean, and gives us an exact answer if we can compute it. So it works well for small to medium data sets, but it becomes computationally expensive when the data set is huge or has a lot of variables. The second approach is iterative optimization algorithm. This is where things get more flexible. Instead of solving it all in one shot, we can gradually adjust the coefficient to reduce the error bit by bit. This is especially helpful for large data sets or when we are using more complex models. Some of the most popular algorithms include gradient descent. This is the classic. We update our guesses for the coefficient step by step, following the slope or gradient of the error function. Stochastic gradient descent, SGD, is a faster, more random version. It updates the model using one data point at a time. Third is Newton's methods. It's a more sophisticated approach that converges faster but requires computing second derivative. So OLS is all about minimizing squared error, and we have two main tools to do it. Either solve it directly with math, or that a computer algorithm search for the best solution. So in the last slide, we talk about OLS, finding the best line by minimizing the squared error between the actual value and the predicted values. Now let's dig into how we actually estimate the coefficients in that line, how we get the slope and the intercept. Let's begin with the general equation of a straight line. Y hat equal to ax plus b. A is the slope of the line. It tells us how much y changes for a 1 unit increase in x. YB is the intercept. That is the value of y when x equals to 0. Now that what OLS does is minimizing this thing, which is summation of y minus ax minus b squared. That is the self-square errors, the square difference between what the model predicts and what the actual values are. To find the values of A and B that makes this sum as small as possible, we take the derivative of that expression with respect to A and B and set them to 0. That is how we find the minimum. So on this slide, you can see the partial derivative with respect to a. We won't do the full derivation here, but it's good to know that it comes from calculus. We're essentially solving for the lowest point in that error curve. Once the math is done, we end up with this formula for the slope and intercept, as you can see here, A and B. So we're using the mean of x and y and the sum of their products and squared to compute these parameters directly. The good news is you will almost never have to do this calculation by hand, but it's important to understand this formula come from minimizing squared error and that they give us the line of best fit. So even though it looks math heavy, it's just solving a classic problem. What's the line that best explains this relationship? So at the heart of it, let's take a step back for a second and ask what's a machine learning model actually trying to do here? At the heart of it, every machine learning algorithm is trying to optimize something. That something is called the objective function. So what's an objective function? Think of it like a global or target the algorithms is aiming for. Some models try to minimize error, others try to maximize accuracy or profit or some kinds of reward. But the point is, there's always a function guiding the learning process. That is the objective function. So when you train a model, it's not just guessing randomly, it's systematically adjusting its parameters to either minimize or maximize this objective. So enter the last function. Now, most of the time, especially in supervised learning, our objective function is actually a special kind of function called a loss function. This tells us how far our predictions are from the actual values. The bigger the loss, the worse the prediction. The model learns by adjusting itself to reduce that loss. You can think of the loss as a penalty for being wrong. There are different kinds of loss depending on the task, regression loss and classification loss. If you are predicting a number like house values, house price, common loss functions include mean squared error or mean absolute error. These measure how far off your predictions are on average. And if you are predicting a category like spam versus not spam, you might use cross entropy loss or hinge loss. This measures how confidently and correctly the model classifies the input. To sum up, the objective function is the overall thing the model tries to optimize. In many cases, this is a loss function, which tells us how bad our predictions are. Training a model just means tweaking it to reduce that loss as much as possible. It's kind of like playing a video game. Your model is trying to get the lowest mistake score it can by making better and better moves. Now let's zoom in on one specific kinds of loss, regression loss. This is what we use when we are trying to predict continuous values, like someone's age, the price of a car, or the temperature tomorrow. There are a few different ways to measure how far off our predictions are from the actual values. Let's walk through the three most common ones. First is MSE. This is probably the most popular loss function in regression, and it goes by a few names: mean square error, or quadratic loss, or sometimes just L2 loss. The formula is the sum of y sub I minus y sub I hat square and sum over I from 1 to n, and then take the average of it. So we take the difference between the actual value y sub I and then the predicted value y sub I hat, square it to make sure negative don't cancel out, and then average all those squared differences. So if our predictions are far off, the squared differences get big, and so does the MSE. It's a good default choice because it punishes large errors more heavily thanks to the squaring. Now, sometimes it's helpful to express the error in the same units as the original variable, like dollars, inches, or degree. That's where root mean square error comes in. Root mean square error is the square root of MSE. Right? It gives you a number that's easier to interpret in real world terms. For example, if your RMSE is 5 and you are predicting house price in thousands of dollars, that means your average prediction is about $5,000 off. Last up is mean absolute error, or L1 loss, MAE. The formula is instead of squaring the errors, we just take the absolute value of each one and then average them. This one is more forgiving. It treats all errors equally, no matter how big or small. It's especially useful when your data has outliers and you don't want those extreme values to skew your result too much. So if you want to punish large errors more, use MSE or RMSE. If you want a simple average error and don't want to overreacting to outliers, then use MAE. They each give you slightly different perspectives on how well your model is doing. Okay, so now let's compare L1 loss, which comes from MAE, and L2 loss, which comes from MSE and RMSE that we discussed in previous slide. Both are used in regression, but they behave differently, especially when it comes to outliers and model optimization. So first, let's look at sensitivity to outliers. MSE and RMSE are much more sensitive to outliers than MAE. Why? Because remember, MSE squares the error. So if there's really big mistake, squaring it make that error even bigger. Let's say one prediction is off by 10 units. MSE turns that into 100. But if it's off by 100 units, it becomes 10,000. So large errors have a huge impact on the overall loss when you are using MSE or MSE. Now, when is that a good thing? If your outliers are important anomalies, like identifying fraud or diagnosing rare diseases, then you want to react strongly to those big mistakes. In that case, use MSE or RMSE. But if those outliers are just bad data or measurement errors, then you probably don't want them messing up your model. In that case, MAE is safer because it treats all errors more evenly. That's why the L2 loss function works well most of the time, but it's always smarter to consider removing or handling outliers first. Second, gradient behavior. Let's now talk about something more behind the scenes, the gradients, or how the loss function helps the model update itself. MAE has constant gradients, meaning it applies the same pressure to adjust the model, no matter how big or small the error is. On the other hand, MSE or MSE has dynamic gradients. The bigger the error, the stronger the adjustment. That makes learning faster when the model is really wrong and gentle and gentler when it's close. This behavior often makes MSE or RMSE easier to optimize smoothly using algorithms like gradient descent. However, since MAE has a flat gradient, it can be a little trickier. So when using MAE, it's a good idea to pair it with an adaptive learning rate, something that can help the model adjust its pace depending on how the training is going. So in summary, when you care about big errors more than smaller ones, or if you want faster and smoother training, or you are okay with being influenced by outliers, or you have already cleaned them up, then use L2 laws such as MSE or RMSE. Now use L1 laws or MAE when you want robustness against noisy or messy data, or you are okay with a slightly slower, steadier learning process, or you want every error to be treated equally. So that is how you will make a good choice between L1 loss and L2 loss. So far, we have talked about L1 and L2 losses, like MAE versus MSE or RMSE. But sometimes we want something in between. That's where Huber loss comes in. Huber loss is basically a hybrid between MSE and MAE. You can think of it as the best of both worlds. It behaves like MSE when errors are small, and like MAE when errors are large. Let's break down the formula here. If the error, which is the difference between prediction and actual, is small, less than some threshold delta, then we use squared error, just like MSE. But if the error is larger than that threshold, we switch over to using absolute error, like MAE. This way, we get the smooth optimization benefits of MSE without being overly sensitive to big outliers. Why does this matter? That little Greek data delta is called a hyperparameter, and it plays an important role when the residual error is less than delta. We treat it as a small harmless mistake, and then we use MSE. When the residual is bigger than delta, we assume it might be an outlier. So we treat it more gently than we use MAE. So with Huber loss, we are not letting the big errors completely dominate the training process, which can happen with MSE. So key takeaway from here is Huber loss is especially useful when you are dealing with data that might have some outliers, but you don't want to throw them away entirely. The curve around the minimum is nice and smooth, which means optimization is stable and gradients behave well. Overall, it's more robust to outliers than MSE, but also more sensitive to small errors than MAE. So if you are not sure whether to use L1 or L2, Huber loss gives you a flexible in-between that adjusts automatically based on how big the errors are. Now let's talk about one of the most fundamental tools in all of machine learning and deep learning, which is gradient descent. Think of this like gradient descent is our way of teaching the model how to improve itself one baby step at a time. So gradient descent is an optimization algorithm. That means it's a method for finding the best possible parameters. In our case, the best regression coefficient that minimize the error. More specifically, gradient descent helps us find the lowest point of a curve, also known as the minimum of a function. The function we are trying to minimize It's usually the loss function. So really, we are using gradient descent to reduce error. Imagine you are standing somewhere on a mountain in a fog. You want to get down to the lowest point in the valley, but you can't see very far. So what do? You feel the slope beneath your feet and take a small step downhill. Then you stop, feel the slope again, and take another step. That's exactly how gradient descent works. It follows the slope, what we call the gradient, of the loss function, and takes small steps in the direction that reduces the error. So let's look at the update rule on the slides. So m sub n is our current parameter. Let's say the slope of our line, right? And L of m sub n is the loss we get when we use that parameter. And then the gradient is the slope of the loss function at that point. Alpha is the learning rate. It controls how big each step is. So this rule just said, take the current parameter, subtract a small step in the direction of that gradient, and repeat. So this graph is a visual of the loss function when we are adjusting two parameters like the slope m and the intercept c of a line. The vertical axis is the loss, how wrong our model is. The goal is to find the lowest point on that surface. Where the loss is smallest, that's where our model makes the best predictions. So gradient descent is simple but powerful. It works well for most differentiable functions, meaning functions where we can compute a slope. Choosing the right learning rate is important. Too big and you might overshoot the minimum. Too small and you might it might take forever to converge. Let's bring everything we have done so far together and look at a visual of how a linear regression model actually works under the hood. Take a look at the diagram in the middle of the slide. On the left, we have our input features, L1, L2, x up to x, x1, x2, up to x sub m. These are the variables we are using to make a prediction, things like age, income, number of years of education, etc. Each of these gets multiplied by a weight, shown here as W sub I, W sub 2, up to W sub m. These weights are the coefficients the model is learning, basically how much each variable should count. We also include a special input 1, which pairs with a bias term W sub 0. Think of this like the intercept in the equation of a line. All of this flows into the summation function. This is where we compute the net input like with the sum of W of X vector, right? Independent variable vector or feature vector. That is the raw prediction of the model. Then we pass that through an activation function. In the case of linear regression, this activation is actually really simple. It's just the identity function. In other words, it does nothing. The result is the prediction itself, which is a continuous output. Then we compare the prediction to the true value, calculate the error, and adjust the weights based on that error during training. That loop is how the model learns. Now, how is logistic regression different? Logistic regression uses the same exact setup up until the activation function. It still takes inputs, multiply them by weights, add them up, and compute a net input. But then comes the key difference, which is the activation function. Instead of just passing the raw score through as is, logistic regression uses a sigmoid function at its activation that squeezes the output into a range between 0 and 1, so the output can now be interpreted as a probability. Since we are working with probabilities and binary outcomes, we can't use MSE anymore. Logistic regression uses a different loss function, usually cross-entropy loss, which is better suited for classification tasks. So both models look nearly identical in structure. The difference lies in what kinds of output you want. Linear regression models continuous output, like predicting a number, while logistic regression models probability or classification output, like yes and no. And that means we change the activation function, identity versus sigmoid, and the loss function, MSE versus cross-entropy. Now let's look at the Python script that can be used to carry out this type of regression techniques. So we are importing some of the most popular Python libraries for data science, such as Pandas, NumPy. So Pandas is our go-to library for handling data. We use it to read in data sets, cleaning them, and explore data. And NumPy gives us powerful support for numerical operations, especially arrays and matrix math, very useful when working with model inputs. We use seaborn and matplotlib to make beautiful and informative statistical plots. And we use scikit-learn to load in data sets, and then also different functionalities such as standardization of our features, doing the model selection, choose metrics to evaluate model performance, like calculating mean square error, R squared, classification accuracy, and more. And we use module called linear model to bring in main models. One is linear regression for predicting continuous outcomes. Another one is logistic regression for classifying binary outcomes like yes, no, spam or not spam, etc. And we also import make pipelines from pipeline module, which help us combine multiple steps like scaling, training into one clean object. This keeps our code tidy and avoids mistakes like data leakage. So altogether, this block of imports set us up to load data, explore it, scale it, spread it, model it, evaluate it, and visualize the result. Right. So all right, so let's begin by loading and preparing our data. We're using the classic Boston housing dataset, which contains features of homes and neighborhoods in Boston, along with the median house prices as the target variable. first we load the data set and convert it into a pandas data frame, so it's easier to work with. We separate the target variable price from the rest of the feature. Then we split the data set into training and testing sets using a 70-30 split. This way, we can train our model on one part and evaluate how well it generalizes on unseen data. You will also notice the Boston data info line at the end, which gives us a quick look at the columns and data types. All 14 columns are floating point numbers, and there are no missing values, which is great. Now that the data is ready, we train a linear regression model. This is one of the simplest and most interpretable model in machine learning. We use linear regression class from scikit-learn, fit it on the training data, and make predictions on the text data. Then we calculate RMSE, root mean squared error, which tells us on average how far off our predictions are from the actual prices. In this case, the RMSE is about 4.6, which means our predicted housing prices are off by about 4,600 on average, assuming price, well, because here price is in thousands. Here we plot the actual prices versus the predicted prices. Each dot represents one house. Ideally, all the dots should line up along that diagonal dash line. That would mean we predicted the price exactly right. You can see the predictions generally follow the line, but there's definitely some spread. This tells us the model is okay, but not perfect, which is to be expected with real-world data. Let's now look under the hood of the model. Linear regression produces coefficients, one for each feature, which tell us how much that feature impacts the house price. For example, we see that the coefficient for RM, which is the average number of rooms per house, is about 3.99. That means if the number of rooms go up by 1, the predicted price increases by almost $4,000, all else being equal. On the other hand, NOx, which measures air pollution, has a larger negative coefficient, suggesting that higher pollution levels are associated with lower house prices. This interpretation is one of the big strengths of linear regression. The model is transparent and easy to explain. Now let's look at residual versus fitted plot. This plot helps us check one of the assumptions of linear regression, that the residuals or errors are randomly scattered. We plot the residuals on the y-axis and then the predicted prices on the x-axis. If the model is behaving well, we should see no clear pattern, just a cloud of points. That's roughly what we see here, although there may be a bit of a funnel shape. If that pattern gets more pronounced, it could suggest that our model isn't capturing all the structure in the data. So in this step, we calculate another key metric, R squared, as we discussed previously. This tells us how much of the variability in the housing price our model can explain. We first compute the sub-squared error, SSE, and total sum of squares, TSS, and then calculate R squared equals to 1 minus SSE over TSS. In our case, R squared is about 0.66. That means our model explains about 66% of the variance in house prices, which is pretty good for a first pass. Now we are going to shift gear and try logistic regression. To do that, we need to turn our problem into a classification task. We convert the price column from a continuous variable into a categorical one using pd.qcut method function. All right, splitting it into two groups, low and high. This creates a binary outcome we can classify, which is exactly what logistic regression is designed for. So then we built a pipeline that standardized the feature and then applied logistic regression. The standard scaled object ensure that all our input features have the same scale, which is important for models like logistic regression that rely on distance and magnitude. However, in this round, we hit a need that we need to work with binary feature, but we have already used qcut to binarize our price feature. So that been taken care of. Then you can just use this model to make prediction. So that is how you can use Python and its library like scikit-learn to perform both linear regression, logistic regression, which are two special cases of GLM, generalized linear regression model, right? So you can also use scikit-learn to perform other GLM methodologies as well.